All right. Let me share my screen first. Okay. Can you hear me still?
Yes, very good.
Okay, excellent. So first of all, welcome to the lecture. And a big apology that I cannot be there in person. I really would have liked to, but mainly it was a visa problem. So I have to give the lecture online. But so I think the nice thing about giving a lecture online is that I would be there and you could like stop and ask questions after the lecture, before the lecture, and so on. So I would encourage you really during the lecture, if anything is unclear, if there are any questions, just interrupt and ask. Okay, that's important. Okay, so what I want to talk about in these lectures is dark matter effective theory. And to be more precise, I should probably say dark matter direct detection effective theory. And what I want to show you is essentially how to calculate the dark matter direct detection cross-section in, let's say, the most one of the most general cases. So assume we have just a dark matter particle with a mass that can be anything you like, maybe not below a GeV. And it can be, in principle, a fermion, a scalar dark matter particle. It can have any type of interactions. And we want to understand how to calculate this cross-section, so cross-section of scattering on an atomic nucleus. And of course, I cannot give you all the details. So my plan is the following. I want to first take a super naive approach. I want to calculate just take a dark matter fermion with a vector interaction. So let's say an exchange of a C prime particle, and then just straightforward calculate the cross section and see how this goes, how far we get. And then we will see we can make a number of approximations, and we can later generalize these approximations, and that is what gives us the effective theory. So effective theory in some sense is just a systematic way of doing approximations so we can actually calculate something. And so I want you to understand, so that's my goal, that you understand kind of the principles, how these calculations work, how we get these cross sections. And then most of these calculations you don't have to do in real life because there's computer code that does it. And I just want you to understand what is in, like, how this computer code works, or what is the basis of this code. Okay. So that's the aim. And let's start. Let me just write down what we're interested in. So what we are interested in is the scattering rate of dark matter particles on an atomic nucleus. So let's say a differential scattering rate, dr by dq. Q is the momentum transfer. Okay, so a particular experiment will be sensitive to a certain range of momentum transfers. It depends on the type of experiment and on the type of nucleus that is used. But that's the general thing so this left-hand side of the equation is what we measure an experiment in principle. And then we want to calculate this, and this rate, first of all, depends on the local dark matter density. So that for us now is just an astrophysical input. And then there's some kinematic factor. So it's inversely proportional to the nucleus mass and to the dark matter mass. And then there will be a cross-section. So a differential cross-section that I write d sigma by dq. So that's the cross-section of a dark matter particle scattering on the constituents of the nucleus. So this might depend on v and the momentum transfer q, for example. And then because the dark matter energy or momentum distribution is essentially given by the velocity distribution of the dark matter in the galactic halo, we need to convolute with the velocity distribution. So this is a factor v f of v, and then we integrate over v. And f of v, again, let's just regard it as an input. You can use just the naive Maxwell velocity distribution or something more sophisticated. That's what we want to focus on is this microscopic cross-section here. So that's something that's given by a certain dark matter model. And in order to test it, so the relation between the experimental rate and the model is this equation. Okay, and we want to calculate this cross section. Okay, so that's the goal. Now let's see if I can scroll down. Yes. Okay. So first part, let me call it just lecture 1. What we want to do is we want to just take a simple model and just calculate this thing. Okay, and to set the stage, let's first get a picture of what happens in the scattering. And I'm sure, since this is the end of the school, probably most of the stuff you heard in the other lectures, but just let's recapitulate and write this down. So first of all, what we need to recognize is that the dark matter particles cannot, so if they're bound in the galactic halo, they cannot be faster than about, let's say, 500 kilometers per second, because this is the escape velocity of the galaxy. If they're faster, they would just escape. So if you compare this to the speed of light, so let's say v of the dark matter particle is about 500 kilometers per second, and in terms of speed of light, that's about 2 per mil of speed of light. Okay, so you clearly see dark matter is non-relativistic, and this whole process is a non-relativistic cross-section. Okay, we can also estimate the energy transfer or momentum transfer in this scattering process. Okay, for this we need a few definitions. So I need to tell you what are the momenta. So let's say we have a scattering, so a dark matter, let's call it chi, comes in, goes out, scatters here on the nucleus. Nucleus comes in, goes out. So let's call this momentum P1 and this one P2. So that's going in, going out. And for the nucleons, I called it K1, goes in, K2 goes out. Okay, and then we define the momentum transfer just as the difference, let's say K2 minus K1. So that's the final nucleus momentum minus the initial nucleus momentum. That's the momentum transfer. And by energy conservation, that's the same as P1 minus P2. Okay, and so now we can estimate the maximum momentum transfer, so Q max. That's just a simple exercise in kinematics. So I'm not doing this exercise, but if you're interested in the lecture notes that you all have, hopefully, there's a little calculation how this is done. So this, the maximum momentum transfer, that's kind of if the dark matter hits the nucleus head on, it's given by 2 times the reduced mass of the system divided by m dark matter times the initial momentum. Okay, so mu a chi is the reduced mass, and that's m a m dark matter divided by m a plus m dark matter. And for let's say for a 100 GeV dark matter particle, this is about 225 MeV. For m dark matter, 100 GeV. Okay, so that's about the range for the momentum transfer. And then if you know the mass of the nucleus, then you can also calculate the transferred energy. And the maximum transferred energy is also small. In this case, it's about 2 keV. Okay, so this is all low momenta, low energies, low energy processes. Okay, and this is why I'm discussing this, is because this allows us to make some approximations, to take the scattering process as non-relativistic and to recognize that these energies and momenta are very small compared to the other scales in the problem, let's say the dark matter mass and the mass of the nucleus, okay? So we will be able to expand in ratios of these scales.
Question?
There's a question?
Yeah, thank you. If we were to do this for the spin-dependent case, things would get a lot more complicated, right? Or would that not come in until a later point in the calculation?
Can you repeat the question? I didn't hear. I didn't understand.
Oh, sorry about that. If we were to do this for the spin-dependent case, would things already get more complicated at this level, or do those effects come in later in the calculation?
If there's a spin dependency, yeah, so this is just the kinematics. That's completely independent. So that's just the kinematics that gives kind of the overall scales of the process, and then the details of the cross section that come in if we have a model. That's right.
Okay, got it. Thank you.
So this will come later. Okay, so that's a good point to continue. So now, in order to actually do a calculation, we need some model. And let's write down a model. I just give you the Lagrangian. So what I want to have is a Lagrangian. Okay, I'm not writing the usual kinetic pieces, but just the interaction terms. So it will look like this. GV, some coupling, and then I have, let's say, a dark matter vector current coupling to a massive gauge boson. And then the quark current is also coupling to this massive gauge boson. So let me write it down and explain it a little bit more. Okay, so that's our simple model. So you can think of this, you have, so in terms of Feynman diagrams, you have a dark matter particle, and then you have some C prime boson, just a vector boson, massive, and this couples to quarks, so something like this. So here I assume that dark matter is a fermion, and it couples to quarks in this way. And I assume it's a fermion exactly so that later we can also discuss effects of spin. But now let's just focus on this interaction. And here I'm assuming, just for simplicity, that it couples only to up and down quarks, let's say, because these are the constituents of the nucleus, essentially. Okay. Okay, and what I want to do now is I want to just calculate the cross-section as we are used from particle physics, let's say. So we essentially take this Feynman diagram, or we calculate the S matrix element for this scattering, and from this we can get the cross-section. Let's just proceed and see where are the problems and where it is easy and where we go. So in order to calculate the cross-section, we need the S matrix. S matrix essentially just gives you the probability if you have a certain initial state given by the masses and the momenta. What is the probability that you end up with a certain final state with like other momenta and masses? The masses will be the same because this is all non-relativistic, so there are no particles produced, they will just then exchange momentum. Okay, so this S matrix is given by, I just write this down so that the conventions are clear. So there's some factors 2 pi to the 4 in the factor of I that is factored out by convenience. Then M is the transition matrix element. So if you square this thing, this will be proportional to the cross-section up to the phase space factors. And then there's also a delta function that just gives you momentum conservation. So there's a delta P out minus P in. So that just ensures that momentum is conserved in this process. Okay, and then, so this the cross-section is given by, so that's just the usual formula. I just write it down. The details are maybe not so important, but let me write everything down. There's some factors. There's a factors from the coupling. GV, that's the coupling of the C prime to the dark matter, and then there's a factor of GV prime, that's the coupling to the quarks. Then, according to the Feynman rules, we need to integrate over the space-time points where this can happen. So we have an integral over d4x, d4y. And then we have we will have a final state. So let's write this like this. A final state will be a dark matter particle with momentum p2, some spin component r primed. So this is a spin 1/2 fermion, so r prime can be plus or minus 1/2 in some direction. And then the nucleus will also have a momentum and possibly a spin if the nucleus has a spin. Okay, then the interaction is given by the time-ordered product of these two currents connected by the gauge boson. So that's chi bar v slash chi at x, and then the hadronic current, which is q bar v slash q at y, plus xy exchanged. And then, sorry, we have the initial state, which is the chi with an initial momentum p1 and spin component r, and the nucleus with initial momentum k1 and spin component s. Okay, very good. So that's just the standard procedure how to write down this matrix element, and now we need to calculate it. So we use the usual Riggs theorem. So we contract the annihilation and creation operators inside these fields for the vector field and the dark matter and the nucleus field with each other as far as possible. So we first of all see if we go to leading order, there are no vector bosons outside. So we can only connect this vector boson with itself. And this will just give a massive propagator. So this contracted vector bosons will give dx minus y equals. So the propagator is given by this term, v of x, v of y. And that's I'm just quoting the usual results. d4k. I should call this k. I should probably let's call it L, because k is already our external momentum. G mu nu divided by L squared minus the mass of the vector boson squared, and then factor e to the minus I kx minus y. So that's just the usual result of quantum field theory. I should say, for a massive gauge boson, there's also another term in this propagator that goes like mu nu divided by mv squared times this additional factor. But this piece is gauge dependent, and you can just generally show that this will always drop out. Essentially, that's related to current conservation. If these currents are conserved, and if you contract this momenta with the currents, this will drop out in the end. So I'm not even writing this down, just for completeness. Okay, so that's one piece. So that takes care of these V fields. Then next we want to take care of the dark matter fields, and then we can contract these external dark matter states with the internal dark matter fields. Okay, in this case that's very simple, because our final states are dark matter particles, and in our interaction we have dark matter fields, so they have the same creation and annihilation operators, and we can just use the usual Feynman rules to contract them. Okay, so in order to do this, we need to recognize, first of all, that we assume that dark matter, like apart from this exchange of this vector boson, we assume that dark matter has no interaction. So it doesn't have a charge, it doesn't have a color charge or anything like this. So apart from this vector exchange, it doesn't interact with the quark currents. And that means that we can just factorize this matrix element into two factors. So we can write, let me use an abbreviated notation here, chi A, and then this chi bar gamma mu chi q bar gamma mu q chi A. We can write this as just chi and then chi bar gamma mu chi in times nucleus out, and then the quark currents and the nucleus in. Okay, it factorizes in this way because there are no interactions between the two once we take into account this vector interaction. Okay, so we need to essentially evaluate these two pieces, these two factors, this one, and then just perform the integrations, and then we are done. Okay, and this piece is easy because there's a chi outside the chi field in here. It will be more complicated for these pieces because here we have quark fields and outside we have a nucleus, so we have to think about how to treat this. So that will be kind of the main problem. But let's first concentrate on this factor. And for this first factor, let's call it 1, we can just use the usual Feynman rules. And then we can write this matrix element as 1 equals, so that's just given in terms of the spinors for the dark matter, as u bar of P2 r primed times gamma mu, and then u of P1 r times another exponential factor. It should probably be P2 minus P1 dot x. Okay. So in principle, these spinors are general solutions of the Dirac equation, but now we can make an approximation because we know that dark matter is non-relativistic, and in this case, these u bar and these u functions are very simple. Okay, so dark matter is non-relativistic, so we can make we just expand and keep only the leading piece in the momentum, and the leading piece in the momentum in this case is just a constant. So we write that u of PR is just a normalization factor, which is the square root of the mass of the dark matter times Dirac 4-component spinor. So R is just the index of these spinors. So C is just if you choose an axis, then C equals 1, 0, which just means spin up along, let's say, C direction, and C 0, 1 means spin down along C direction. So that's just the non-relativistic Pauli spinor that you know from quantum mechanics. Okay, and then there will be plus corrections, but these corrections will already be suppressed by powers of the momentum transfer divided by the dark matter mass. So we can just neglect them. We just need the first piece. So these are like small corrections and we don't need them. All right, so now these spinors have a simple form, and we can just insert them here. And so now we just need to know what this gamma mu matrix is, and the gamma mu matrix is given by, let's say, 1 plus Pauli sigma E. Okay, that's a slightly weird notation, but I hope you know what I mean. So the 0 component is just the unit matrix, and the spatial components are given in terms of the Pauli matrices, where you have a plus sign here and a minus sign here. And then we need to remember what this bar means. The bar means, so u bar equals u dagger times gamma 0. Okay, and now we can just plug everything in. And we see that this expression is actually quite simple. So we get this u bar gamma mu u is essentially C transposed. Sorry, I should write like this. C transpose, then times this gamma 0, which is just a unit matrix, then times this gamma mu matrix, 1 plus I, 1 minus sigma I. Sigma I are the Pauli matrices, and then C. And you see this is C transpose times, let me write like this, I forgot the factor of m dark matter. So that's m dark matter times xi transpose 1 plus sigma Pauli plus xi transpose 1 minus sigma Pauli. So you see the terms with the Pauli matrices, they drop out because they come with an opposite sign. And all that is left is just m dark matter time 2 times m dark matter times xi dot xi. And xi dot xi is just a delta function. That's just delta, let's call it delta RS. Okay, let's see if I did this correctly. Okay, I should call this delta r prime r because that's how we called our spin variables. And then since the spatial components dropped out, only the zero component remains. So I write here the Kronecker delta mu 0. Okay, so only the zero component of this current contributes. And then we have this factor e to the I p2 minus p1 x that I forgot here. Should be here also. Okay. Okay, so we see, so that part was relatively easy because we can go to the non-relativistic limit. Okay, so that's just essentially given by 2 times the dark matter mass times Kronecker deltas. Okay, any questions here? Okay, seems not to be the case. So let's now look at the other current. So the other current, so we have an external nucleus and we have internal quark fields. So we cannot use the usual Feynman rules because the outside state is like complicated bound state of quarks with virtual quarks, with gluons in it, with up and down quarks, and inside we have this quark current. So what do we do? So first of all, so there are 2 ways to proceed in principle. So one could just write down the expressions for this current and insert the definitions of these fields, and then do lots of algebra with the Dirac spinors and so on and so on. And then you would find, if you did this, so for 2, you would find that Q bar gamma mu Q is essentially has the form, you can bring it to the form A dagger A minus B dagger B, where A dagger creates quarks and B dagger creates anti-quarks. And then what this gives you is just, you see, so this operator, that's just a number operator that counts quarks, and that's a number operator that counts anti-quarks. So this is just the number of quarks minus the number of anti-quarks. Okay, so that's essentially what the result is, but in order to get the prefactors right, that's a lot of work. And what we want to do instead is we want to use a trick of a type that we want to also use later. And the trick is to use a symmetry. Okay, that gives us this result much quicker. And the symmetry in this case is just the baryon number conservation. And what we will see is that this current is just, so this current is just the baryon number current. And since it is contracted with the dark matter current, and the dark matter current has this Kronecker, which picks out only the zero component, similarly here, only the zero component will contribute. And that is actually, and the zero component of a conserved current integrated over a whole space is just a charge. And in this case, it's just the baryon number. So this current essentially gives us just the baryon number of the external states. Okay, so that's the trick that we want to use. Yeah, so let me just write down in formulas what I just said. So what we recognize is that the zero component of this current integrated over space, so the 3y. And now let's be a bit more careful and sum over up and down quarks of Q bar gamma mu q. That's just the baryon number. Okay, and yeah, so in the lecture notes, I hope you all have the lecture notes. I have every now and then I put some exercises to explain some details. So I don't want to talk now about this about Noether currents and conserved currents and charge, but we can discuss this in the discussion session if you're interested. And if you want to look at this, there's an exercise where you're supposed to derive this current. So if you have never seen this before, or if you want to refresh your memory, it's maybe a good idea to do this exercise. And there are also the solutions in the end. So if you want to get a hint how this works, you can look in the solutions and we can discuss this. Just don't want to get lost in details here. But that's the essential idea, that we can recognize this hadronic current as the baryon number. And so this means that we can evaluate this hadronic current. So for this factor 2, we can just write A, I'm leaving out the arguments, and then sum over U and D, Q bar, gamma 0, Q is just given by momentum. So that's just given by, so there's an exponential factor that comes out. So if you're interested about this exponential factor, then you have to pay a little bit more detail to the attention to the details, and this explained in the lecture notes. I'm not doing this here; it costs too much time. But essentially, there's a normalization factor, which is just 2 times the zero component of the momentum. It's just the zero component because we take only the zero component into account. And then this factor is just the baryon number, and the baryon number of a nucleus is just the atomic number A. So A is the atomic number. It's just the number of baryons in the nucleus, essentially, so protons and neutrons. And then delta S primed S if the nucleus has a spin. Okay, and in the non-relativistic limit, the zero component of the momentum is of course just the mass. That's the energy component, so that's just ma. Okay, so that's the second factor. And now we just need to combine everything and do the integrals. All right, so I'm just writing down what we have, collecting everything. So we have this S matrix element equals -4 I GV G primed V M chi MA. So M chi and MA just are essentially the normalization factors that we just talked about. Then we have delta R primed R, delta S primed S for the spin components. And then we have the integration that we didn't do yet. So we have one momentum integration from the gauge boson propagator. And then we have the 2 spatial integrations, d4x, d4y. We have the factor L squared minus mv squared from the propagator. And then we have a bunch of exponential factors that we picked up along the way. So that's a minus I L x minus y, e to the I p2 minus p1 x times e to the I k2 minus k1 y. Okay, and these integrals are very simple because first of all, you see that there's no x dependence apart from these exponential factors. And if you do an integral over these exponential factors over all space, that just gives you delta functions, Dirac delta functions Okay, so this gives just d4L divided by 2 pi to the 4. Then you get two delta functions, 2 pi to the 4 delta 4. So you need to collect the terms with the x's. So this one, and this one. So that gives p2 minus p1 minus L. And then there's another one where you integrate over y. So that gives another factor, 2 pi to the 4 delta 4. And now we have k2 minus k1 plus L. And now you see the momentum integration is also trivial because we can just use it to eliminate one of the delta functions. So that, again, that just gives 2 pi to the 4. And then that just gives us the momentum conservation. So 2 pi 2 minus pi 1. Or let's write it in a nicer way. Pi 2 plus k2 minus pi 1 minus k1. So that's just momentum conservation. And of course, this factor L squared minus mv squared, which just becomes 1 over, let's say, p2 minus p1 squared minus mv squared. Okay. Okay, so now things look already very simple, but we can simplify it even more by looking in more detail at this propagator factor, which still has a momentum dependence, but we can also expand this factor in, because this momentum transfer compared, remember, this is a few hundred MeV at most, whereas this mediator we assume to be much heavier, that's at least a few GeV, or let's say 100 GeV or TeV, so it's much, so this is much larger than this momentum transfer squared. So we can also expand this. So we can just write this as a Taylor series or geometric series. So let's call it the momentum transfer Q. So we have Q squared minus mv squared. I can just factor out, let's say, minus 1 over mv squared times 1 over 1 minus q squared over mv squared. And that's just minus 1 over mv squared times, and now this is just a geometric series, so that's 1 plus q squared over mv squared plus higher terms, but we neglect all these terms. We just keep the 1. So that's, we neglect this and we neglect all these higher terms. Okay, so we just keep the 1 over m squared piece. Okay, let's see. So now we have the S matrix element equals 4 times A, 4I times A, GV primed over MV squared, M chi, M nucleus, delta R prime R, delta S prime S, and then this 2 pi to the 4 delta momentum delta function. And then by definition, remember we factored out this factor of 2 pi to the 4 and I and delta function. If we factor this out, this just gives us m. Okay, so m equals, it's just 4a GV prime m chi ma divided by r delta S prime S. Okay, so that's the transition matrix element. You see it has a very simple form. And in order to get the cross-section, we just need to square this thing. And then we need to sum over all the spins. So more precisely, we need to sum over the spins in the final state because dark matter experiments don't measure these spins separately. And we need to average over the spins in the initial states because we don't know them. So what we need is, if we have now, let's assume we have a nucleus with a spin 1/2, then we have a factor 1/2. Then we have two spin states for both the dark matter and for the nucleus, and we get a factor 1/4 from averaging. And then we just sum over R primed, SS primed, square this matrix element. And the sum is, again, easy because the spin dependence is just these Kronecker delta functions. So that just gives 16a squared GV primed squared, dark matter squared, MA squared divided by MV to the 4. And then we can get the cross section if we want. It's just 1 over pi mu chi a squared. That's again the reduced mass, a squared GV primed squared divided by MV to the 4. So here I just use the standard formula from Peskin and Schroeder to get the cross section.
I have a quick question.
Yes.
So if we were thinking about dark matter as a composite particle, could we use a similar symmetry argument that we did with the standard model component of this calculation?
Again, it's because there's kind of an echo, so it's hard for me to hear. Could you repeat the question, please? I'm very sorry.
Sorry about that. No worries. If we were thinking about dark matter as a composite particle, could we use a similar symmetry argument to the one that we did with the standard model particles?
Right. Yes. Good point. So here, exactly. So here I just said the dark matter part is easy, but what I of course assume this dark matter is just an elementary particle. If that's not the case, if dark matter is composite, then you will have to deal with the same complications as you have to deal with in the hadronic sector. And here, okay, maybe that's a good point to recapitulate a little bit what we did. So first of all, we have seen we could use a very simple symmetry argument, namely baryon number conservation, but that's because we assumed a vector interaction. That's kind of by design. I chose this example because it makes the calculation easy, because you can just see that the interaction is just proportional to the baryon number. That's how we use this trick. We saw also by the explicit calculations that in the leading approximation, the spin dependence completely drops out. So that's just a contact interaction. So there's no dependence on spin. And you see what this means, what comes out of the calculation. So the cross section is proportional to a squared. So that's sometimes called the coherent enhancement. So if this is spin independent, the dark matter sees all the nucleons in the nucleus at once, and you coherently sum over all the interactions on the nucleon. So that's this factor a squared, and there's no spin dependence. And we used our trick for the vector interaction. If this is not a vector interaction, but let's say you exchange a pseudoscalar or a scalar particle or an axial vector or whatever comes to your mind, then we cannot use baryon number conservation. But as I will explain later, we will still be able to use symmetry arguments to at least parameterize these currents in a general way. Now, if dark matter is not a point particle or elementary particle, but also has to be treated as a composite, then you would have to do the same thing. So either you are lucky and it's a vector interaction, and then this would just count essentially the dark matter nucleons, or like the dark matter constituents of the composite, or it's something more complicated, and then you also have to just parameterize it in a more general way. Because I would assume if dark matter is composite, it probably has some strong interactions that you cannot treat purely perturbatively. If you have a perturbative model, I don't think there are bound states in perturbative models. So yeah, you have to do something similar. Okay, sorry, that was a long-winded answer. I hope it was clear.
Yes, it was. Thank you.
Okay. Very good. My suggestion is, since we have 90 minutes of lecture, and this in some sense finishes the first part of what I wanted to say, is to have like a few minutes break, just breathe some air, take a deep breath. I'll just stay here, so if you have more questions, you can just ask. And let's say in 3 minutes, we continue.
Recording stopped.
So there you go. I think you can restart.
Recording in progress.
Okay, go ahead.
All right. So, welcome back after the short break. So let's quickly recapitulate what we did. So we calculated the cross-section of a dark matter scattering on a nucleus in a simple example. And the example was that we have a Dirac fermion dark matter. And the only interaction between the dark matter and the nucleus is the exchange of a heavy vector particle. So something like a C primed in the C prime model, so, or like the C boson or a heavier cousin of the C boson. And then we did the calculations, and we could actually do this calculation on this hadronic object of the nucleus by making a few assumptions, or not assumptions, a few approximations. And the approximations were actually the following. So first of all, we expanded, so we did an expansion of the propagator. And we could do this because Q squared was much smaller than the mass of the mediator. The next approximation which we did is we took the non-relativistic limit of the dark matter current, or dark matter interaction, dark matter current. And we could do this because the momentum transfer was also much smaller than the dark matter mass. Okay, so that's essentially, that's the only limit on the dark matter mass. In principle, dark matter could be anything, but if dark matter is too light, if it gets of the order of the momentum transfer, then our techniques will not work. So what I'm talking about works if dark matter is heavier than about a GeV, so that this expansion makes sense. And the third approximation was use baryon symmetry or baryon number conservation for the hadronic current. And this was kind of, let's say, a bit of an accident that we had an exact symmetry that allowed us to calculate this exactly. But what we want to do now is we want to take each of these approximations that we did and generalize them to a general strategy that will work for all cases. Okay, so we will talk about the expansion of this propagator. We will talk about how to take the general non-relativistic limit of a dark matter current, even if it's not a vector current. And then we will also talk about what to do with the hadronic currents. So the hadronic currents, this problem is the most complicated because we need to both take the non-relativistic limit, and we have the complication that there are low energies in the non-relativistic low energy regime. These baryons, they're just bound states of quarks, so they're non-perturbative objects. So we need to see how to deal with this.
I have a quick
there's
question.
kind of a yes.
Sorry to interrupt. Thank you. So my understanding was that in our simple model here, that third point, the using baryon number conservation was exact, but is there an approximation that we're making? Is it not exact in this simple model?
In this simple model, it was exact. It was exact. Like the okay, in some sense, we still made an approximation by going to a very low energy and treating the nucleus as just, a point object, just counting the constituents. If the dark matter is energetic enough, it can start probing the structure of the nucleus. It won't break the nucleus apart, but it can see that there's a distribution of the nucleons inside the nucleus. So we made a little bit of an approximation. So in general, as we will, maybe I can just say it now, as we will see, you should describe this interaction of the dark matter with the nucleus by a form factor, which is just a function of q squared. And in leading approximation, if we can just the leading term of q squared for the vector current, that's just a constant. It's actually just the baryon or the atomic number of the nucleus. If dark matter is more energetic, you get let's say a slight momentum dependence. So that's an approximation that we did. But apart from this, everything was exact.
Got it. Thank you.
So for more general currents or interactions, there will be additional approximations. So we have this form factor, so this momentum dependence from the fact that the nucleus is actually an extended object. But if dark matter is relatively low energetic, it basically doesn't see this. But we don't have an exact symmetry like baryon number conservation. We'll talk about this. So the symmetry which will replace this is an approximate symmetry, and it's the chiral symmetry of QCD. We will talk about this. All right, so that's kind of the outline of the remaining part of the lectures. And we'll start with the easiest one, which is expansion of the propagator. So what we have seen, so let me call this local dark matter interactions. So what we will assume is that what we will assume is the following. We will always assume that dark matter is neutral under the standard model gauge interaction. So it has no electric charge, and it has also no weak charge, and it has no weak charge is not so important, but it has no QCD charge, no color. Okay, so the only interaction comes from heavy new particles. Okay, and these heavy new particles, they could be either heavy vector bosons, or they can, like in our example, but they could have, instead of vector interactions, they could have V minus A interactions, or just axial interactions, or like any combination of this. Or you could have a scalar exchange. Also for the scalar exchange, there are different possibilities that you could have, like just a scalar interaction, or you can have a pseudo-scalar interaction, so something that is even or odd under parity, or any combination of these two. Okay, so there are different possibilities. But what we will always assume is that the mediator mass is larger than the momentum transfer. Okay, that's like one of our assumptions, and it's I think a very good assumption, because we haven't seen any of these mediators, so there must be, unless the couplings are extremely tiny, small, I think they must be heavy enough so that we didn't see them at colliders. Okay, so that's a reasonable assumption. And if we make this assumption, we can always do this expansion of the propagator like we did for the vector interaction. And these propagators, they have always this form. It's some q squared minus m squared, and then there's some numerator here. And this numerator depends on what type of vector this is. So this could be either a g mu nu, or this could be just a 1, or it could be like something. So these are the two most important cases for scalar and vector interactions. And then we write this always as a numerator. Just think of g mu nu. So numerator, sorry, I can't write. Numerator plus that is suppressed by q squared over 2 and higher. So we can always make this approximation if this condition is satisfied. And what this gives us, as we have seen, so if we make this approximation, then there's no momentum dependence in this interaction, and that's just a static interaction. So that's in our example, that's look just like an interaction that we can write as chi bar gamma mu chi times q bar gamma mu q. That would be an axial vector interaction. You can do v minus a, then you get something action of the W boson. You can this could look like something like this, just chi bar chi, q bar q, or pseudoscalar exchange. This gives you something like chi bar gamma 5 chi, q bar gamma 5 q. You can also mix them. You can have something like chi bar chi, q bar gamma 5q, or whatever. It's just depends on your UV model. But there's just a certain number of possibilities that you can write down. And the idea is to just write down all these possibilities and to give them names. And the names we give them is just, these are, we call them effective operators. It's just a fancy name, but what it means is just it's a contact interaction that is valid in the approximation that the mediator mass is much higher than the momentum transfer. Okay, and okay, so you can just list all these operators and give them names. So for example, this one that we considered has the name, essentially we gave it a name. You can call it what you want, but one way of giving it a name is to call it Q161. It's just a number. 6, what the 6 means I'll explain soon, and Q is just the flavor of this quark current. So there can be a Q1 up, a Q1 down, Q1 strange, whatever your mediator couples to. And the strength of the coupling was in our model given by this GV primed. We can also just leave it general. It can just come with any number here. So in our case, the coefficient was actually given by minus GV primed over M vector squared. That's kind of an important point. It comes with 1 over M vector squared. It has to, because if you count the dimensionalities of these fields, so these are all fermionic fields and they have mass dimension, so fermionic fields have mass dimension 3/2. So if you sum them up, you see that this has mass dimension 6. And that's why I wrote a 6 here. Okay, so that's the mass dimension. And we know, so how do these mass dimensions work? So what we want, in order for the dimensions all to work out correctly, we know that the Lagrangian has to be a scalar. Lagrangian is a scalar, so it has mass dimension 0. Okay, the Lagrangian is written as an integral over all space of a Lagrangian density. So that has this integral, so this has like 4 spatial dimensions, and by Fourier transformation that has 4 inverse mass dimensions. So this thing goes like 1 over m to the 4 from the integration. So there's a mismatch between the 6 and the 4. So you need another inverse square of a mass, and that's this one. So it means that a dimension 6 operator, as we call this, the coupling has to come with 1 over m squared. And we saw this explicitly. That's just the heavy mediator that we integrated out, as we say. Yeah, so in general, we can write, so by just listing all the possibilities, we can write this Lagrangian as a sum over all, let's say, all operators. Let's give this an index A. So that just enumerates all these different possibilities of operators. And then, you know, the more fields you attach, the higher the dimension of this operator is. So there's also an operator dimension D that we just talked about. So we sum over all this, and all of them get coefficients that in principle are arbitrary. Once you have a model, these coefficients are fixed. So like in our case, this coefficient was fixed to like this coefficient of this operator 1, let's say Q, up, down, 6. Was just given by this value that we calculated. Okay, what does this hat mean? Hat means just sometimes you want to factor out this suppression scale explicitly. So you can write C d a hat equals C d without a hat, and then divided by lambda to the power of d minus 4. So the minus 4 comes because the integration gives you automatically a power of 1 over m to the 4. So all the remaining powers to make this a scalar has to be in the scale. Okay. I don't know if this became clear, but to sum this in a simple way, that's just a way of writing the most general interactions that are valid at low momentum transfer. Yeah, we can write it in this way in terms of these local operators with coefficients that you can either measure an experiment by doing dark matter experiments, or you can calculate them in a model. Maybe one more comment. So this is the interaction that we looked at before, and I want to later discuss another interaction that is a bit more non-trivial, and it will be this one. And by convention, there's a factor of I here to make this currents Hermitian. And this, I will also give this a name just for later reference. And if you write down all these numbers, there are several of them. So this has number 8. So that's Q8. Q again is just the quark flavor. And I want to write this as dimension 7 because I want to write a factor of a quark mass here. That's just a convention, but that's kind of a general adopted convention because this is a scalar current. So this scalar currents or scalar operators, they tend to mess with electric symmetry breaking. And in most models, these interactions get a further suppression. So that's why I write this as dimension 7. Dimension 7 means that it is suppressed by lambda to the power 3. So that's something like mq over lambda times 1 over lambda squared. You don't necessarily need to include this factor of q. You can drop this factor. So it has to have 1 over lambda squared because the fields are dimension 6. But in most models, you will pick up such a factor. So it's by convention included. Okay, that's just a side comment, not super important, but what is important to remember this operator. So this operator is if you exchange a pseudoscalar between the dark matter and the quarks, and this operator is if you exchange a massive vector. That's what we discussed before, and that's what we want to discuss later, because this, as we will see, will lead to a spin-dependent interaction and also to a momentum-suppressed interaction, and we want to see how this comes about. Okay. Good. I think that's all I wanted to say about the local interactions. Are there any questions?
Yes, sorry, I have a question. So this capital lambda that appears in the coefficients of the general expression is always related to the mass of the mediator? No, is something more general?
Yeah, in some, yeah, roughly speaking, yes. So you see in the example, it's related to the mass or the inverse mass squared of the mediator times the couplings. So if the couplings are order 1, then it gives you an idea of the mass, but typically the couplings are smaller than 1. So okay, so you have this relation between this scale.
Okay, thank you.
Yeah. Plus my comment from before, there might be other couplings that are actually ratios of scales if you have electric symmetry breaking, so you can pick up more factors like this. But typically, as a rule of thumb, it's good to think of this scale as just the mediator mass up to a, I don't know, coupling factor. Yeah.
I also have a quick
Yes.
question. Yeah, thank you. So for that last operator you were talking about with the exchange of the pseudoscalar, you said that can mess with our electroweak symmetry breaking. But because we're dealing with this low momentum regime, couldn't you just set your cutoff below the electroweak symmetry breaking scale?
Yes, yes. You can even think of these operators. They have, yeah, it's just a convention. Maybe I shouldn't have said so much about it. Maybe it was confusing. It's just the way the operators are written, and I want to, I want to be consistent with what's written in the papers. So let's just accept it that it's there. And if this doesn't come out of your model, then you just rescale everything by an inverse factor, and then this thing drops out. Let's not get worried about this factor. Let's just keep this quark mass there. In some sense, it just redefines what you mean by your coefficient. I never said what these coefficients are. So these are called the Wilson coefficients. Wilson coefficients. So in some sense, just a convention. So these are called Wilson coefficients. You can just calculate them in the way that we did before. If you have a given model, you can just calculate what they are. Yeah, and these Q's are the local operators. Okay. More questions? Okay. So very good. So let's now just use these instead of a vector model. Now we just think of these local interactions as our model, and we want to continue from there. Okay, and then in the lecture notes there are references with like complete lists of these operators, like basically all the possibilities that you can write down up to a certain mass dimension. And maybe one more comment now that I'm talking about it. In principle, of course, there are infinitely many such operators that you can write down, but you see, if you increase the mass dimension, you always increase the power of this suppression scale lambda. So if this power gets very large, again, these effects will be super tiny because they are suppressed by a very large power of a heavy mass. So we can just drop them. So again, rule of thumb is to just keep the lowest dimension operators. Okay, and the two I want to focus on are these two, Q1 and Q8. And okay, so that's that. In order to do this, so that kind of takes care of this one, expansion of propagator. That's done. So the next thing that we want to do is to take the non-relativistic limit, and we want first to discuss the dark matter current, because we will again assume that dark matter is like a point particle, elementary. So that will be relatively easy, and then we can discuss complications of bound states later once we understand the non-relativistic limit. And this non-relativistic limit of the dark matter, or of an elementary dark matter, has a name, and it's called heavy dark matter effective theory. And I should say, this was essentially just stolen from the flavor physicists, because they had to treat essentially B mesons at low energies, and the B quark is still relatively heavy at low energies, so they had to do a similar effective theory. So we can just take over this whole formalism just for an elementary dark matter which doesn't have strong interactions. It's much simpler because you don't have the complications of the strong interactions. So that's where all this formalism comes from. Okay, so what is this formalism? What am I talking about? So the underlying problem is the following: we have a external dark matter particle that scatters on a nucleus, and it's non-relativistic. And here above, for the case of the mediator, we could just do a simple expansion in 1 over m squared. And it was simple because this mediator particle never appeared as an external state. So we can just approximate everything in terms of a contact interaction. Here, for the dark matter, we cannot just neglect, or it's like a bit more non-trivial to neglect inverse powers of this heavy mass, because the external particle just has its mass. So it's kind of, you cannot just drop parts of this mass that it has. Okay, so one has to be a bit more careful. And sorry, let me see. What we want to do is the following. Okay, so let's say we have a form momentum of this external particle. This will be completely dominated by the mass term. So let's say mass of dark matter times the velocity, for velocity. And then there will be a small piece, let's call it k. Okay, so k mu is something small. So v mu is the for velocity in the, let's say in the lab frame, that's just the 1, 0, 0, 0. Okay, so there's, it's just, so this form momentum is completely dominated by the energy, and the energy is completely dominated by the mass because it's non-relativistic. And what we want to do is we want to scale out this mass piece. Okay, so that all momenta, so what we want to do is we want that momenta are small, because we want to expand in, let's say as before, in momentum squared over mass squared. But if this momentum has a heavy mass in it, then expansion like this, that's order 1. That doesn't make any sense. So we have to get rid of this large piece. So that's what we want to do. For fermions, there's a further small complications, because relativistic fermions are described by Dirac spinors, which are 4 components, but only 2 of them survive in the non-relativistic limit. So because essentially 2 of these components describe a particle, and 2 of these components describe the antiparticle. But if we are in the non-relativistic regime, we will never create an antiparticle because there's not enough energy available. So we want to also get rid of these antiparticle components. And to do this in a systematic way, that's what we need heavy dark matter effective theory for. And we do this as follows. So first of all, we make this split. We make this heavy mass dependence explicit in this way. And then we take the dark matter field, let's call it chi of x, and we do 2 things. First of all, we scale out, we multiply by a scale factor e to the I m chi. Okay, m chi equals m dark matter. I'm switching between the 2 all the time, but that's always the same. Chi is the dark matter. E to the minus I m chi v dot x. Okay, so we'll see what this factor does. This factor, essentially, I can tell you what it does. It removes this this m piece. And then we split this dark matter field into 2 fields that we call small chi v of x plus capital chi v of x. And it will turn out that small chi v will be the particle components, and the capital will be the antiparticle components, and we don't need it. We need to get rid of it somehow. Okay. And what is this split? I should be more explicit what the split is. So chi v of x, so the small one is e to the I m chi v dot x times 1 plus v slash half times the original field, chi of x. And capital chi of x equals e to the I m chi v dot x 1 minus v slash half chi of x. Okay, chi of x is the original field. So you see this, we split in this way. So if you insert it here, you see you get back what we have here. And I introduced, so these are the scale factors that get rid of this mass piece. And then these 1 plus v slash, so v, remember, is just the for velocity, and v slash, that's just the notation v contracted with a gamma matrix. These essentially project, these are projectors that project onto the particle components of these spinors. Okay, in the lab frame where v mu equals 1, 0, 0, 0, these projectors are just 1 plus gamma 0 plus minus gamma 0. Okay, and this is just written in a kind of, okay, if you're not in the lab frame, then it's the general expression. That's something that is also done in usual quantum mechanics. That's called a Foldy-Woodhausen transformation. In case you have heard this, that's essentially the same thing. You just want to pick out always the particle components. Okay, that's what this projector does. Okay. Okay, good. Now we have split the field, but we are not finished. We need to get rid of the chi field, and for this we need to do a little calculation. Okay, and what we do is we just take this. We start with the Dirac equation. The Dirac equation for a free dark matter particle, free because it doesn't have any interactions apart from contact interactions. So the Dirac equation for this field is just I d slash minus m chi acting on chi of x equals 0. Okay, that's just the Dirac equation. And what we do is we multiply this from the left with the projector 1 minus v slash half. Oh, I should write from the left, so this times this equation. Okay, so we get 1 minus v slash half I d slash minus m acting on chi equals 0. Okay, so now what we want to do is we want to commute this projector to the right. Okay, so here this is just a scalar, so nothing happens, but here we have so here's a gamma matrix, here's a gamma matrix, so we need to remember this, the Clifford relation, which tells you that gamma mu plus gamma mu equals 2 g mu nu. Okay, which means if you commute to gamma matrices, you will pick up a minus sign and you will get a correction term from this g mu nu. So that means if we commute this thing past this operator, we get something that is I d slash and now 1 plus v slash over 2. And then we get a piece that is minus 2 times v dot d. And here's a 1 over 2, and there's a 2 from this relation. So we get minus I v dot d. And then this mass piece is just a scalar, so we can just move that past it. So m chi 1 minus v slash over 2. Okay, again acting on to make a nice chi of x equals 0. And now what I want to do, so this chi, I want to insert our relation here. So we split this, we factor out this scale factor and split it into these two components. So I want to insert this here. So I write this as e to the minus I m chi v dot x times chi v of x plus capital chi v of x. Okay, equals 0. So now the next thing is we have derivatives here, and these derivatives will act now on both this scale factor and this and the fields. So if I want to move them the scale factor out, so I can divide by the scale factor. So I will pick up terms that come from the derivatives acting on the scale factor. Okay, so I can write this as, now it gets a little bit more complicated still. So I move this to the left, e to the minus I m chi v dot x. And then I pick up terms from this derivative. So I have I d slash that now acts on these fields, and that get a term from acting on this exponential, which is just m chi v slash, and then this factor 1, this projector 1 plus v slash over 2 minus, again here I pick up a term from the derivative, which is just plus m chi, and then minus m chi 1 minus v slash half times chi v plus capital chi v equals 0. Okay, so this looks now pretty complicated, but now we'll see that this simplifies nicely, because you can easily calculate that 1 minus v slash times 1 plus v slash equals 0. And by definition, the small chi v comes with a 1 plus v slash, and the capital chi v comes with a 1 minus v slash. So if you act with the kind of the opposite projectors on it, this will just drop out. So 1 minus v slash acting on this one will be 0. 1 plus v slash acting on the capital one will be 0, and so on. So this simplifies. And we can divide by the scale factor. So we get the following: I d slash plus m chi v minus I v dot d plus m chi v plus capital chi v equals m chi capital chi v. So I dropped this term and I dropped this term. And now you see there are more terms canceling. This term cancels against this term, and this whole thing simplifies to I d slash plus m chi. I d slash minus I v dot d chi v minus I v dot d plus 2 m chi v equals 0. And finally, I v dot d plus 2 m chi x v equals I d slash perp chi v. And this d slash perp is just this thing. I d slash perpendicular. It's kind of the d slash minus the component in direction of v. It's called the perpendicular derivative. It's just a name. Okay. So, and now we take this equation, and okay, so this is a differential operator acting on this capital chi field, and now we just multiply this whole equation with the inverse of this differential operator. and then we get chi, capital Chi v equals I d slash perp divided by I v dot d plus 2m chi v. Okay, and so now we have, so with this calculation, we have expressed these antiparticle components in terms of the particle component lengths. So we can just use this to eliminate capital Chi. And then we can express everything in terms of the small chi, and small chi are the dark matter particles as opposed to antiparticles. And this inverse, like this inverse operator here, you should think of this as a Taylor series of this expansion. So now I see it's already 5. So maybe that's a good place to stop for now. And then next time we will continue, and we will use this relation and insert it into our expressions for the currents and see how this gives us the non-relativistic limit for the currents. Are there any questions at this point?
Any questions here or on Zoom? No, I don't see any for the moment. So thank you very much, Joachim. Thank you for the lecture.
Thank you.
And so we'll see you tomorrow. Thank you.
Yes, we'll continue tomorrow. Thank you.
Recording stopped.